Hello students, so today we are going to talk about a very important topic of your NEET curriculum, that is radius ratio. Now this topic is included in the chapter solid state, and you will be finding a very small piece of one line or maybe two lines in NCERT. But everywhere if you search the PYQs, you will get at least one or two minimum questions from this particular topic. Okay, so this is something called radius ratio, and it has a very useful applications. Okay, we will talk about that applications later in one separate video, but today we are going to understand what exactly the radius ratio is and how you will determine the radius ratio of a particular solid having a particular definite geometry. Okay, now see, by the definition you can say that it is nothing but the ratio of the cation to the ratio of the anion. Okay, so it is nothing but the radius of the ratio of the radius of the cation to the radius of the anion. Okay, and it is defined by the capital R. It is defined by capital R in the fifth suffix small r. Okay, now see, it is very obvious that every time that we know that the cations will be always smaller in radius, as there is a higher effective nuclear charge which actually increases the electron nucleus attractive force, make the size smaller, whereas in case of anion the electron repulsion makes the size larger. So as we can see that if the radius is r plus and if the radius is r minus, so always you remember that in case of the radius of the cation will be always lesser than the radius of the anion, and which actually makes the radius ratio always basically your lesser than 1. That means if I tell in this way that what will be the maximum value of the radius ratio, that will be always tends to 1. The R max value will be always 1. Now you can see here there is a list of different geometries, important geometries such as linear geometry, planar triangle geometry, tetrahedral, octahedral, BCC geometries. So in these geometries you will find the maximum value of the radius ratio is 0.999, which is almost near to 1, right? Okay, and if I see this one very carefully in this way, okay, right? So if I see here one thing very carefully is that every geometry corresponding to each and every corresponding coordination number. Now if we are able to calculate the radius ratio of any geometries, or let's say any experimentally if we are able to calculate, using that data and using this table we can easily find that what will be the corresponding coordination number, and once we know the coordination number we can easily able to find it out what is the formula of the corresponding lattice. So that we will talk later somehow. Now let's say if I have a planar triangle geometry shape or geometry, whatever you prefer to say, then what will be its limiting radius ratio? The limiting radius ratio, it should come around 0.155. Let's see, let's take an example, dekhte mathematically it comes or not. Okay, now so this is a very specific planar triangular geometry where these bigger circles are your anions, and this small one is the cation. Now you see that this is an isosceles triangle, that means all of the angles are 60 degrees, right? So if this is your 60 degree angle. Okay, now see here, this corresponding cation, this will be the radius of the cation, this small amount will be the radius of the cation, right? Okay, and if I look in this way, and if I draw a line from here, this part will be your radius of the anion. This part will be your radius of the anion. That means specifically this distance, this particular distance if I talk about, this is basically nothing but my r plus plus r minus. Okay. Now similarly here, let's take out this triangle here. Let's take out this triangle here and see. Okay. So this is the point and this is my corresponding r plus plus r minus, right, which is nothing but this distance. Okay. And the corresponding what we have here, let's draw a perpendicular here, draw a perpendicular here, and this is basically what? This is basically, if I think in this way, this particular point, this is this particular point, that is this point. So this is A, B, C, D, E. Let's say this is your F. So this is your A, this is your F, okay, and this is your point D, right? Now what is this AF distance? What is this AF distance? This AF distance is basically nothing but your R minus, right? So what we can say then? Then we can say that AF by AD, AF by AD is basically your R minus by R plus plus R minus, correct? A wave by AD, so basically A R plus R minus by R plus plus R minus, and this is what? Nothing but, if your this total angle is your 60 degree, if this total angle is 60 degree, then beta this particular angle is your 30 degree angle. So this is nothing but is equal to my cos of 30 degree, cos of 30 degree, right? So which is equal to nothing but your root 3 by 2, nothing but is equal to root 3 by 2. Now if I solve this one, what I will get here? So I am just reversing R plus plus R minus divided by R minus, that is equal to 2 by 1.732, okay, or what we can write, R plus by R minus is equal to 2 minus 1.732 divided by 1.732, and if you solve this one, this is what? This is nothing but my radius ratio. This is nothing but my radius ratio, and if you solve this one, the value you will get 0.155, which is nothing but the limiting radius value of the planar triagonal value, planar triagonal. That means that in case of, by this way you can also, by same method using some cos angle, sin triangle, you can also calculate the limiting radius ratio of different geometries also, and that should actually match with this particular values, that should actually match with this particular values, right? So this was the overall concept of the what is radius ratio and how we can determine the radius ratio. Now in the next video you check in the link where we will discuss about the what is the application of the radius ratio, and using that how you can determine the stability of the lattice, how you can determine the defects in the lattice, and exactly using this radius ratio concept we will arrive that how the Schottky defect is happening in the solid, how the Frenkel defect is happening in the solid. Okay, so till then, if you like this one, share with your friends, and if you have any questions or any comments, don't feel free to write in the comment section. So till then, from my side, everyone, thank you.